Okay, let us start. So remember, we have seen a concept called relative degree of a system. So this is related to how many times that we need to differentiate the output y before there appears a relationship between the input and the output of the system. So we have seen that this is actually, if your system is controllable, this is going for a system in the following form: x dot is equal to f of xu, y is equal, for a system, it is in general in this form: f of x plus g of xu and h of x. This is between 1 and n. Okay? So here, therefore, here this n is nothing but the size of x. Okay? X is composed of n elements: x1, x2, going until xn here. So here, this theory, the relative degree, is also applicable to linear systems, in addition to the nonlinear system. Because a linear system is nothing but a special case of a nonlinear system. That is why we can actually look at the relative degree of a linear system. So we have, in this case, we have x dot is equal to ax plus bu, and y is equal to cx. In this case, we see that these functions are actually comparable to their nonlinear counterparts. So here, f of x is ax, and here, g of x here is b, and finally, h of x is equal to cx. Okay? So we see that in this case, this linear system is a special case of an affine system. So for this linear time invariant system, we could actually define the transfer function. It is in general in the following form: s to the n minus 1, b2, s to the n minus 2, going until bn, divided by s to the n plus a1 s to the n minus 1, going until an. So this is the transfer function of such a system. And I could actually find a state space representation for this transfer function. And here I will use the controllable canonical form state space representation. It is looking like this. So I have x dot is equal to a times x plus b times u, and y is equal to cx. Okay? When you write a controllable canonical form state space representation, we fill in the b vector by all zeros except for its last element, which is 1. And then if we look at this c vector, in that case we would fill in from the numerator coefficients. Okay? b1, b2, going until bn in reverse order. We write them into c. And when we look at the A matrix, in that case, we're going to be writing these denominator coefficients in the following form: minus a1, minus a2. In reverse order, I will write their negative into the last row. The main diagonal is going to be 0 except for the last element, and the first super diagonal is going to be 1. This is, and I will have zeros everywhere else. This is a state space representation in controllable canonical form. And that was actually what was taught in the course EE404. So now I'm going to consider a third order system, and based on that third order system, we will be looking at the relationship between the relative degree and the transfer function of that system. So let us say we have a third order system. Well, this is a specific case of a third order system when n is equal to 3. So let us say the transfer function is b1s squared plus b2s plus b3 divided by s cubed plus a1s squared, a2s plus a3. Okay? In this case, my state space representation is going to be looking like this. X dot is equal to, in this case, the sizes will be just 3. Y is equal to Cx. If I fill in these matrices, I will have minus A1, minus A2, minus A3. Main diagonal is 0 except for the last element, and the first super diagonal is 1, and it is 0 everywhere else. And 0, 0, 1 is the B vector, and B1, B2, B3, it forms the C vector. Okay? In this case, we will be looking at some specific cases. I will have 3 cases, and based on these, we will try to determine the relative degree. So case 1 is, let us say B1 and B2 are both equal to 0, and let us say B3 is not equal to 0. Okay? Because if B3 is equal to 0 as well, in that case, the transfer function would be equal to 0. That means that we have an uncontrollable system in that case. We want, the relative degree is going to be infinite in such a case. So here, let us say that B3 is non-zero, and I have here B1 and B2 are both equal to 0. So we have G of S is equal to, in that case, B3 divided by the denominator, A1S squared plus A2S plus A3. Okay? So we have this. So now I'm going to be looking at the equations of this state space representation. I have the first state equation, x1 dot is equal to x2, and x2 dot is equal to x3. That is what I'm reading from these equations. And x3 dot is equal to, I have minus a3 x1 minus a2 x2 minus a1 x3 plus u. Okay? These are what the equations are. And I have y is equal to b3 x1 plus b2 x2 plus b1 x3. Okay? So now, the number of poles and number of zeros of this transfer function are given as follows. The number of poles, p is equal to 3 in this case. And I see that here, the number of zeros, z, is, what is the number of zeros of this? It is just 0 in this case. Okay. So here, let us try to determine the relative degree of the system. So I will start from the following equation. Y is equal to, I already know that B1 and B2 are equal to 0. That means that this equation will turn into B3 x1. So we see that in this equation, there is no input. That is why the relative degree of the system is not equal to 0. So I will start differentiating here, and I will get y dot is equal to B3 times x1 dot. Okay? So when I write B3 times x1 dot, I can read from the state equations x1 dot is equal to x2. So I have B3 times x2 here. I see that I don't really see the input in this second equation either. Okay? That means that the relative degree of the system is not equal to 1. Okay? Remember, the relative degree is the minimum number of times we need to differentiate the output y before there appears a relationship between the input and the output. So here, there is no input in this equation still, so I need to continue differentiating. So I have y double dot is equal to b3 times x2 dot. Okay? And in this case, x2 dot is equal to x3. That actually gives me b3 times x3. Okay? Which means that in this equation, we don't have the input again. That means that the relative degree is going to be even higher. So y triple dot is going to be b3 times x3 dot. And that is going to give me the right-hand side here. b3 times minus a3 x1 minus a2 x2 minus a1 x3 plus. And in this case, we see that the output actually the input actually has appeared in this equation. That means that the relative degree of the system in this case is going to be 3. This is the minimum number of derivatives we need to take before there appears a relationship between the input and the output. So this was the first case. Okay? And here we are trying to explain a relationship between the relative degree and the number of poles and number of zeros of the linear system. So here let us look at case 2. B1 is equal to 0 and B2 is not equal to 0 and B3 is arbitrary. So that is the second case. Okay. So if I look at the transfer function in this case, g of s is going to be b1 is equal to 0. As a result here, I will have this term disappearing. b2 is non-zero, so this term will be there. b2s plus b3 divided by the denominator. In this case, if I look at the number of zeros, z is equal to 1. So irrespective of what b3 is, this transfer function will have 1, 0. Okay? And when I look at p, the number of poles, it is going to be 3 again. In this case, the output equation is going to be looking like this. So I have y is equal to, if I substitute b1 is equal to 0 there, it is going to be b3 times x1 plus b2 times x2. Okay? That is. So relative degree is not equal to 0. There is no input in this equation. So I will start differentiating. Y dot is equal to b3 x1 dot plus b2 x2 dot. Here, from the state equations, I could actually read b3 times x1 dot is equal to x2 plus b2 times x2 dot is equal to x3. Okay? And I still no sign of the input here. So I will differentiate once more. Y double dot is equal to b3 times x2 dot, but x2 dot is equal to x3 plus b2 times x3 dot. x3 dot is going to be given from the equation there. Minus a3x1 minus a2x2 minus a1x3 plus. So we see that in this case b2 is non-zero and there is this input here. There appeared a relationship between the input and the output here. That means that the relative degree of the system is going to be actually 2 here. And it was here. The last case we will consider is going to be the case when b1 is non-zero. And I will have b2 and b3 arbitrary. Okay? They can be 0. They might not be equal to 0, etc. So in this case, our transfer function is in the general form. Okay? That is what I have. And in this case, if I look at the number of zeros, it is 2. The number of poles is equal to 0. In this case, there is no simplification in the output equation. Y is equal to b3 times x1 plus b2 times x2 plus b1 times x3. Okay. No input in this equation, so relative degree is going to be larger than 1. So I have b3 times x1 dot is equal to x2, plus b2 times x2 dot, which is x3, plus b1 times x3 dot is going to be given from there, minus a3x1, minus a2x2, minus a1x3, plus. In this case, what is the relative degree? It is just going to be 1. So we see here a relationship between the number of zeros and number of poles of the transfer function of a linear system and the relative degree of that linear system. What is the relationship? Based on these two cases. So in this case, relative degree is 3, so we have P 3 and Z 0. We have P 3 and Z 1 there. So we can actually write the following. Relative degree of a linear system is P minus Z. Okay? So here, this is the number of poles minus number of zeros. Okay? So how many poles of the system are there? There are more than the zeros of the system. That is what the relative degree is for linear systems. But we cannot use this for nonlinear systems. Why? Does this relationship make any sense in a nonlinear system case? Does this relation, so, yes. For a nonlinear system, we won't have a transfer function. That means that poles and zeros are not actually defined quantities, let alone their numbers. So for a nonlinear system, the only way to check the relative degree is to differentiate the output. So here, let us see the theoretical part of feedback linearization. Design. Feedback linearization based design of tracking or servo controller for an affine system. Okay. So we have, in this case, we have already seen this design on some example system. On the pendulum, we have seen this design procedure. Now we are actually going to be seeing the general theory on an affine system. So we have g of x q and y is equal to h of x given like this. There is an aim here. Okay? We would like to design the controller. What it means is that what is control? Selecting the input of the system such that the output makes something that we wish. Okay? So we are going to try to design our controller. Okay? We will try to choose u such that y does something that we would like. So here the aim is we would like the output y of t to follow the reference input r of t. In other words, we want the error. We have an error signal E of t, which is r of t minus y of t, to go to 0. Satisfying some performance measures. Satisfying some performance requirements. Okay? These performance requirements are going to be based on desired pole locations. So let us go over the design steps. So the first step is to determine the relative degree RD of the system. That is the first step of the design. And in determining the relative degree of the system, we will differentiate this y. Relative degree is going to be between 1 and n, and in that case, I will start differentiating this output until an input term appears. So when we reach the relative degree of the system, this notation is going to mean the derivative order here. Okay? Y to the ith order derivative is going to be defined like this. Okay, that is the definition. This is di times y times d t to the I. Okay, that is the ith order derivative of the output. And when we determine the relative degree of the system, the equation that we obtain is going to be looking like this. In general, the RD order derivative of y is going to, of course, contain the input of the system. Okay? So here, the right hand side of this equation is going to be formed out of some terms, and these terms would be looking like as follows. There will be some linear terms in y, and there will be some nonlinear terms in x1, x2, going until xn here, okay? And there will be input-related terms on the right-hand side. Plus input-related terms. So here, these terms, the mathematical equations for these terms would be given as follows. The linear terms in y is going to come from y and its derivatives. Okay, so we will have alpha 0 y plus alpha 1 times y dot going until alpha rd minus 1 y to the rd minus first order derivative. These are the linear terms in terms of y that we can get on the right hand side. Obviously, sum of alphas or all of alphas might be equal to 0. Sometimes we won't have some linear terms in y. Okay, so here, depending on which coefficients are actually non-zero, we will have these type of terms. So these terms are linear terms in y. Okay? And I will continue about the nonlinear terms. It is going to be a function f1 of some state variables. Okay? So these are going to be f1 of x1 to xn. These are nonlinear terms in x1, in the state variables. Okay? Plus the input related terms. Plus g1 of x1 going until xn times u. The good thing about using an affine system here, here is that the input is going to come here and enter this equation linearly. Okay? That is going to be the good thing about an affine system. In the general system, x dot is equal to f of xu, when you try to find the relative degree, the input here can enter into this equation nonlinearly. Okay, so then you might not be able to solve that equation for the input. That is why we are using an affine system. in the feedback linearization controller design. And this is nothing but the input related terms. So this is the first step of the design. And in the first step of the design, what we do is that we determine the relative degree of the system and we get this equation. Okay? When for any such system, we need to be able to put that equation into this form by taking the derivatives of the output with respect to time over and over. Okay? So after this equation is obtained, we are going to go to the second step. So collect linear terms in y on the left. So we're going to take all of the output related terms, linear output related terms, to the left hand side. So I will just write y to the rd order derivative, and I will write the lower order derivatives here. There will be minus alpha rd minus 1 times y rd minus first order derivative, and these are going to continue with minus signs, minus alpha 1 y dot minus alpha 0 y. This is going to be the left hand side of the equation. And then I will have the right hand side. It's a very, very simple step. So the third step is going to be the following. Choose the input U. This is the controller design part. Okay? Choose U such that the right hand side becomes the following. R to the rd order derivative. R is the reference input. Minus alpha rd minus 1. R to the rd minus first order derivative. And these are continuing minus alpha 1 r dot minus alpha 0 r. Plus, there will be some error related terms here. So this is going to be k0 e plus k1 e dot going until k rd minus 1 e rd minus first order derivative. Okay. So we're going to try to, by choosing the input u, that is our controller design. By choosing the input u, we are going to try to convert this right hand side into this. Okay? We will always be able to do this. Okay? So what does this require? In other words, choose u as follows. So I'm trying to make the right hand side here exactly equal to this. Okay? So before I can do anything, I need to cancel these coefficients in front of u. Okay? That is actually why I'm going to place 1 over g1 x1 x2 going until xn into as a scalar multiplying the right hand side. Okay? So this term is going to cancel this coefficient in front of u. Okay? And then what I have to do, I need to add these right hand side terms here. Okay? The right hand side terms are going to contain the following: r to the rd order derivative minus alpha 1 r dot minus alpha 0 r. Okay? This is going to be the first part of the controller, and I will have the other terms on the right hand side plus k0 e, K1 E dot going until KRD minus 1. Error-related terms here, okay? I have added I first cancelled G1 here, okay? G1 is cancelled, and I add the right-hand side terms that I require on the right-hand side. And there is an extra F1 here. What I have to do is that I need to cancel this from by using the input, okay? So I'm actually adding minus F1, X1, going until Xn into my controller, and that is going to complete my controller design. Okay. So here, let us try to look at what these terms are. These first terms related to the reference input, they are going to be called the feed-forward terms. Okay. They are going to be related to the feed-forward controller. Okay. So here, these second terms related to the error, they will be related to the feedback controller. They are called feedback error control. And the last term is related to feedback linearization. These are these three parts of the question.
The previous example that we had covered in previous lecture,
yeah,
had a sign Y.
Sorry. Yes. Yes.
Is that?
It's going to be in this one. Y can be written in terms of the state. So here, in general, there is no harm here to include Y here in these nonlinear terms. But this is already quite general, because Y is already H of X in this case. Okay. So here, but there is no harm in including Y. Okay.
So is it required that F can be nonlinear, but H is linear?
No, it doesn't have to be. So here I can put here I can here put Y into this F1. Okay. So for example, these values might be just the following. Let us say Y is equal to x2 squared. Okay. And here let us say that. Let us say here that f1 is given in the following form: x1 cube plus exponential x2 plus let us say y squared. Okay. If f1 is given in this form, okay. So in that case, you could always write this f1 in terms of x1 and x2 only. Okay, you can actually substitute this y is equal to x2 squared into this equation, and this would be a function of x1 to xn only. Okay, so it's not a loss of, there is no loss of generality in removing y from this equation, but there is no harm including y there either. Okay. So here, this is the three-part controller that we can design by using feedback linearization. So here, there is an important distinction between the example that we have solved with the pendulum. In the pendulum case, this was sine y only. Okay, so in the pendulum case, this function was sine y. Okay, but here in the general theory, this is going to be a function of the states. In my input, I need to subtract this. In control systems, we generally measure the output. So subtracting sine y is not really a problem. It's not really a problem for me, because we already observe the output of the system. That is how the output is defined. These are the quantities that you are trying to observe. But in the general theory, the thing that I need to subtract here is going to be dependent on the state variables. Okay? So for being able to subtract it, I need to know the values of those state variables. Okay? That is an important distinction, and that is a weakness of feedback linearization controller. Okay? Why is that? Because we need to know the whole state variables, all of the state variables in this F1 in order to be able to make this subtraction. Okay? That is going to mean that either I need to put sensors in my system to observe all of the state variables, or I need to design an observer in order to be able to estimate these elements. Okay? So this is actually a weakness of the feedback linearization controller. The terms that I need to use in my controller are not only functions of the output. They are functions of the state, which means that I need to be able to observe the state before I can use that controller in a satisfactory manner. So here, what is this output going to do? I will substitute it in this equation, and I'm going to obtain the following equation. Okay? So when I substitute this input into this equation, G1s are going to be cancelled, and then F1s are going to be cancelled, and I will get this right-hand side. So the right-hand side is going to be exactly this. So what is the equation that I'm going to get? I'm going to get y to the RD order derivative minus alpha 1 minus alpha RD minus 1 y RD minus 1 minus alpha 1 y dot minus alpha 0 y is equal to, the right hand side is going to be exactly this equation. So I will write exactly the same terms. So the feed forward part is going to be a replication of the output related terms here, with exactly the same coefficients, but with the reference signal. This is the first part of the right-hand side, and the second part of the right-hand side is going to be the following. So I have plus K0E, K1E dot, going until K RD minus 1, E to the RD minus first order derivative. So now let us make some manipulations on this equation. I will take all of these R-related terms to the left-hand side. And these are going to be giving to me the following: y minus r signal times rd minus rd order derivative, okay, minus alpha rd minus 1, and I will write here y minus r rd minus first order derivative. Okay, so these are going to continue minus alpha 0 y minus r. It is y minus r itself. Okay? That is equal to, I have K0E, K1E dot going until K, RD minus 1, E to the RD minus first order derivative. So here, I know what y minus r is. We have defined the error signal as r minus y, which is the negative of these differences. Okay? That is why I could actually obtain the left-hand side as follows in terms of the error signal. I can actually put here a minus sign, okay? And then here I can write e to the rd order derivative minus alpha rd minus 1 e to the rd minus first order derivative minus alpha 1 e dot minus alpha 0 e. Okay? That is going to be my left-hand side in terms of the E signal. Okay? So this is E is nothing but minus y minus r. Okay? So for each of these signals, I substitute minus E, minus E, minus E, and I could take minus signs all out. Okay? In the front. That is equal to K0 E plus K1 E dot going until K RD minus 1 E RD minus first order derivative. So now I can take all of the left hand side into the right hand side to get the following equation. So I will get e to the rd order derivative, and I will get k rd minus 1 minus alpha rd minus 1 times e to the rd minus first order derivative. I can take all of the left hand side into the right hand side to write the following. Okay? Going until I have k1 minus alpha 1 e dot plus k0 minus alpha 0 e is equal to 0. Okay? This equation is only going to be dependent on e, and it's going to be a homogeneous linear differential equation in terms of. And after obtaining this, we are going to have the last step of the design. This is going to be place the poles of the error dynamics at the required positions. In the open left half plane to make E of t go to 0 as t goes to infinity with the desired properties. So here, from this error equation, I could actually obtain the characteristic polynomial of the error dynamics. Okay? The characteristic polynomial of the error dynamics is going to be the following: s to the rd plus k rd minus 1 minus alpha rd minus 1 to the s to the rd minus 1. Okay? I'm writing the characteristic polynomial of the error dynamics. Okay? Plus k1 minus alpha 1s plus k0 minus alpha 0 is equal to 0. This is the characteristic equation of the error dynamics. Of the error dynamics. And then what are the poles of the error dynamics? Poles of the error dynamics are the roots of this polynomial. Okay? And what I'm going to do is, let us say that this is d of s. This is the characteristic polynomial of the error dynamics, and we are going to have a d bar of s. Okay? This is going to be a desired polynomial, desired characteristic polynomial. Okay? And this desired characteristic polynomial is going to be formed out of desired pole locations, s minus p1, s minus p2, going until s minus pn. And these p1, p2 going until pn, they are desired pole locations. So if we have some performance requirements in the tracking controller design, we need to convert those requirements into desired pole locations. And after converting them into desired pole locations, I can obtain my desired characteristic polynomial. Okay? This desired characteristic polynomial is going to be formed out of the desired pole locations, and it's going to be another polynomial that is going to be an RD order. This is actually nothing. This largest order here is just RD. Okay? Because in this case, this polynomial will have RD roots. That actually means that my desired characteristic polynomial will have RD roots. Okay? So that is why this desired polynomial is going to be in the following form. So I have s to the rd plus drd minus 1, s to the rd minus 1, going until d1s plus d0. Okay? This is the desired characteristic polynomial with its coefficients. Now what am I going to do? I need this polynomial to have these roots. Okay? So I'm going to equate the polynomials. Okay? So we will just equate d of s is equal to d bar of s. Okay? And this means that the coefficients should be equal. We know these d's. We know these alphas. What we have to find here is these k's. Okay? Those k's are going to be obtained as follows. Ki minus alpha I is going to be obtained by setting these differences to bi. Okay? And this is true for I from 0 to RD minus 1. Okay? That is going to give us the unknown K values, so Ki's, the unknown feedback error controller gains are going to be obtained by di plus alpha. We will know di based on the desired characteristic polynomial, and alphas are going to come from the system equations while we try to obtain the relative degree, and Ki's can be calculated using this equation. And this type of setting here, and this type of finding the coefficients, it is called pole placement. Yes, exactly. They are coming from the system dynamics while we try to determine the relative degree. So how does the controller looks like? So we have x dot is equal to f of x plus g of x u, and y is equal to hx here. This is the output y, this is the input u. Okay? And my controller in this case is actually obtaining the following equation. So we have here this 1 over g1 function here with the states. Here, the state variables are all measured, okay, and they can be taken outside the loop. Okay, so that is what state variables are. And into g1, I substitute this x here, okay, and here my controller is going to be obtained by adding three types of terms. Zaten 30 olmuş saat herhalde burada. Bunu çizmeden bitirsem daha hakkaniyetli olacaktı sizin zamanınız için. So here in the next lecture, we're going to be drawing the overall block diagram of the controller here, which contains three distinct terms. Okay, but that's going to be all for today. Thank you very much.